Okay, we are going to look at the elevator problem, which applies to anything that can accelerate upwards or accelerate downwards, like an elevator. Now, in real life, if we're talking about an elevator, it doesn't accelerate for any great long period of time. The elevator's at rest, there's no acceleration. It accelerates to get up to a certain speed, and then it travels at a constant speed, or again, there's no acceleration, and then it slows down. So for the period that it speeds up and the period that it slows down, that's the only time there's an acceleration. But if we looked at a person, let's say we have a person, and they are standing in the elevator, and here he is. Oof. Now, let's say the person's just standing in the elevator and the elevator's not moving, so we're waiting the door to close, whatever. And we could say that there's two forces acting on this person. There's the force of gravity down, and there is the normal force up. Once in a while this pen doesn't write. Alright, here we go. It is the normal force up. Good. Now, Newton's second law tells us that the sum of the forces equals mass times acceleration. And the sum of the forces in this case, well, the sum of the forces in this case is the normal force plus the force of gravity. I'm going to put the signs in, or I'm going to add these together, note in their direction. So really it's going to be the normal force minus the force of gravity. Now that's what equals the sum of the forces, and that's what's going to equal the sum of the forces in all the cases the person's in the elevator, because when they're in the elevator, gravity's pulling down and the floor is pushing up, and that's it, right? There's no other forces involved in this. What's going to change at different times is mass times acceleration, and actually even more specifically, the person's mass isn't going to change. The only thing that is going to change is the acceleration. So when the person's standing there, let's get rid of that. When the person's standing there, there is no acceleration, or we'd say the acceleration is zero, right? If the person's standing in the elevator and the elevator's not moving, acceleration zero, so 0 times anything is 0, which means the sum of the forces add up to 0, which means the two forces are the same. Whatever we could calculate gravity to be, that's what the normal force is. Now, let's say that the doors close and the elevator starts going up. Now, it starts at rest and then it goes to a new speed, so there's an acceleration. And let's say that the person's on the bottom floor and they're going up to a higher floor, the 20th floor or something like that. So as soon as the doors close, there's an acceleration, and there's an acceleration upwards. So the acceleration is positive. So the normal force minus the force of gravity, that doesn't change. Sorry, I don't know why this keeps doing that. Equals mass times acceleration. Or if I wanted to find the normal force of this person, how hard is the ground pushing up? Well, then that's going to equal mass times acceleration plus the force of gravity, because the ground has to push harder, because not only is it canceling out gravity, it's causing the person to accelerate, right? So both things are happening. So the normal force is equal to these two things. We could say that the person's apparent weight is equal to these two things, because that's how hard the ground has to push in order to hold them up or to stop them from falling through the surface, which means, for effective purposes, he weighs more now than he normally does. Okay, so the elevator accelerates upwards to get up to speed, and then for most of the time it's traveling, it travels again at a constant speed. It doesn't really speed up or slow down through most of its trip. Well, it's traveling at a constant velocity. That's good, which means its acceleration is 0, so the sum of the forces adds up to 0, and again, the normal force and the force of gravity are equal to each other. So elevators at rest, these two forces are equal to each other. Elevators traveling at a constant velocity, these two are equal to each other. The only time they're not is when the elevator's accelerating, like the first or the middle part there where we said that the elevator's speeding up. Now let's look at the last part. So we're almost at the floor that you want to get out at. So the elevator has to do something. It has to slow down and come to a stop. Well, that means that it's a negative acceleration or it's an acceleration down. If you're moving up, then you need an acceleration in the downward direction to slow you down. So over here we will now have, well, still the left side doesn't change because those are the forces, but it's going to equal mass times a negative acceleration, or negative mass times acceleration. Wherever we put the negative isn't such a big deal, but this is a negative number, so it's going to be a negative acceleration. So that means that the normal force is going to equal the force of gravity minus mass times acceleration, or the ground is not pushing as hard as the gravity is pulling down, which makes sense. The downward force is winning, which is going to cause you to slow down. So without using any numbers, right, we have 4 different situations, twice where the forces are equal. When the elevator is accelerating up, the normal force has to be equal to the sum of these two. And when the when the elevator is slowing down or has a downward acceleration, it has to be equal to the difference of these two, because we keep changing the direction of acceleration. Again, we haven't really changed the left side of the equation. It is the right side of the equation that is varying for this problem.